what? Extra bit I'm going to include along with my data bit. So here CRC is called an n-bit CRC, and when it is checked the value, then it is n-bit. When my both the inputs are low, I'm going to get low output. When my both the inputs are high, what's my output? It is low, zero. Hello friends, a warm welcome to my new session on the data link layer. I am your Revathi ma'am, faculty from the Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence, MYSURU. So dear student, before going to start my today's session, let me to recall the topic what I have discussed in my last session. In my last session, I started with checksum. Why we require checksum? In order to detect the error. And we have discussed how to create checksum at the sender side as well as at the receiver side. Dear student, please make a note here. At the receiver side, after getting checksum value, if all the checksum fields are 0, then that indicates that the data is not corrupted. If any one of the field includes 1, then that indicates that the data bit is corrupted. So receiver is not able to accept the data. So receiver is going to reject the data if any one of the bit includes 1. Now in my today's session, I am going to discuss polynomial codes. That is nothing but the CRC. So what is CRC here? That is nothing but the cyclic redundancy check. So I'm going to have this cyclic redundancy check. In the sense what? I'm going to have redundant bit and I'm going to fill the 0. How many zeros I'm going to fill? 3 zeros. Anyway, dear student, this is very important topic from the examination point of view. Let's see the CRC. So, what is CRC? That is cyclic redundancy. So, what is this redundancy? That's nothing but the redundant bit. Redundant bit in the sense what? Extra bit I'm going to include along with my data bit. So here cyclic redundancy check is a method used to detect accidental changes. During the data transmission, the data bit may corrupted accidentally. Now, to detect which bit is corrupted, we are going to have cyclic redundancy check. So, here cyclic redundancy check uses generator polynomial. So, here in this CRC, we are going to use polynomials. So, that is itself known as generator polynomial. To find the CRC bit, we are going to use polynomials, and at the sender side I am going to use polynomial, and at the receiver side also I am going to use polynomial. So dear student, if I consider this example, this is linear polynomial and this generator polynomial represented key value. Now in my error detection technique, to represent key value, I am going to use generator polynomial. So dear student, if I consider the polynomials like 1 plus x square plus x cube. Okay, wherever I am having the x term, for that I am going to write the binary numbers. So here x3 is nothing but the x3 bit is present. So it is true. So 1 I'll write. And x2 is 1, but I don't have any x1 term. So I'll write 0 and I'll write 1 as it is. Now what is the key value? It is 1101. There are certain situations I'm going to have the polynomials like 0x cube plus 1x square plus 1x plus 1. In this situation, what is my key? 0, 1, 1, 1. So, this is my key. Okay, to generate the key, I am going to use the polynomial. Here, see here, I am going to have another example. X square plus 1. Which term is missing here? That is x1. So, 1, 0, 1. So, what is the key here? Here the key is 1, 0, 1. And if I consider this example, I am going to have the x to the power 3 plus x plus 1. Oh, fine. See here. x3 is present. So, I will write 1, but I am missing x2. So, I will write 0. X term is present. So, 1 and 1 is present. It is 1. So, what is my key? 1, 0, 1. Now, dear student, where n is nothing but the number of bits in the data. Okay. Here, n is nothing but the number of bits in the data that to be sent. Then, k is nothing but the key. Number of bits in the key obtained to generate the polynomials. So, n is nothing but the number of bits, where k is nothing but the number of bits in my key. Okay, the most commonly used polynomials are, okay, if it is n bit, then n minus 1 CRC. See here, the bit length is 9, so I am going to use CRC 8. If I have 17 bits, what is the CRC I have? That is 16. If I am going to have 33 bits, then CRC is 32. If I am going to have 65, then what is the CRC? That is 64. So, here CRC is called an n-bit CRC, and when it is checked the value, then it is n bit. Okay, for example, if I am going to have the 8 plus 1, okay, it is 9 bits, then what is the CRC? 8 CRC or CRC 8. If it is 17, then CRC 16. If it is 33, then CRC 32. If it is 65, then CRC 64. Now, dear student, if I consider computer network, we have the sender and we must have the receiver. And in my sender side, I am going to have CRC generator, and in my receiver side I am going to have CRC validator. Now, in my sender side, okay, generation of encoded data from data and generator polynomial. So, here I want to generate the data as well as I want to generate the polynomial, that is nothing but the key. Okay, now see here, the binary data is first augmented by adding k minus 1 zeros at the end of the data. So, dear student, whatever the data I have, for that I am going to add 0, 0, 0. In the sense what? Based on my k. So, what is k here? K is nothing but the key. So, dear student, think that I am going to have the key 1, 1, 0, 1. So, what is my k? K is nothing but the 4. Now, how many zeros I want to add? That is k minus 1. That is 4 minus 1. It is 3. Another situation that my k is 5. Okay, fine. Now, think that I have the data bit 1, 0, 1, 0, 1. Okay. Now, what is the augmented data I want to add, or what is the CRC I want to add here? That is 5 minus 1, it is 4. I want to add 4 more bits to my data bits. Then I am going to perform modulo 2 binary division. I want to perform modulo 2 binary division. To perform modulo 2 binary division, I want to consider XOR gate. I hope you are familiar with XOR gate truth table. And I am going to write the XOR gate only for 2 to the power 2, that is 4 bits. Okay, fine. Now let me to construct the table here. Let me to construct the table here. Okay, I have two possible inputs, A and B. And what are the combinations I can have? 0, 0, 0, 1, 1, 0 and 1, 1. Over. Then XOR or A XORed with B. Okay, fine. Now, listen here how to write the output. I want to consider odd number of ones. See, 0, 0, even number of 0, so I'll write 0. Here 0, 1, I have odd number of 1, it is 1. Here 1, 0, I have odd number of 1, so I'll write 1. Here I'm going to have even number of 1s, so I'll write 0. This is the truth table of XOR gate. Okay, so when my both the inputs are low, I'm going to get low output. When my both the inputs are high, what's my output? It is low. That's nothing but the 0. And another situation when my any one of the inputs are high, then I'm going to get high output. So I'm going to perform modulo 2 binary division to divide binary data. Okay, append the remainder. So whatever the remainder I'm going to get at the end. So what I want to do, I want to append that remainder with my data. Anyway, at the beginning only we have generated CRC. Initially what we did, we added zeros. Now I want to replace that 0 with my CRC. Okay, fine. Now if I consider receiver side, our receiver is going to perform binary, that is modulo division 2. That is binary division. It is also known by modulo 2. So once again we are going to perform XOR gate output, or we are going to consider XOR gate output. Okay, and we are going to focus only the remainder. At the end, if we get all the zeros, then we are going to accept the data. Otherwise, we are going to reject the data. In the sense what? After performing division, okay, if we get in my remainder place all the zeros, then that indicates that the data bits are not corrupted. So accept the data. If I get 1 instead of 0, then what's the meaning? That indicates that the data bits are get corrupted. So reject the data. Anyway, dear student, let me to explain CRC with an example. Okay, see here. This is the example for no error in transmission. So no error in transmission in the sense what? There is no bits are corrupted. None of the bits are corrupted. See here, what is the word I want to send? That is 100, So what is the key? That is 1101, and that is generated by using polynomial generator. So it is generated by using polynomial generator. Okay, fine. Now, which is the polynomial generator? That is 1 plus x square plus x cube. So here, or x3. 1, 1, x term is missing. So it is 0, 1. Okay, so x1 term is missing. So it is 0. And I'm going to have the data bit 1 0 0 1 0 0. Okay, fine. Now, according to the algorithm, okay, how many zeros I want to add, that is depends on my k. That is depends on my k value. Okay, fine. Now, see here, what is the length of the key? It is 4. So, 4 minus 1, it is 3. So, how many bits I want to add? It is 3. So, dear student, let me to write the example here. 1 0 0 1 0 0. Fine. Then what is my key? 1 1 0 1. Okay, fine. Now I'm going to add 3 more zeros here. Now what I want to perform? I want to perform division. That is binary division. Mod 2. Okay, to perform mod 2, what I want to remember? I want to remember XOR gate truth table. So 0 0 0 0 1 1 1 0 1 1 1 it is 0. Okay, I want to remember this truth table. Now ones are 1 1 0 1. See the truth table. When my both the inputs are high, output is 0. So 1 1 it is 0 0. When I am going to have odd number of ones, it is 1 0. Okay, fine. Now I want to bring this 0 here. I'll write it here. Ones are 1 1 0 1. Okay, fine. So odd number of 1. Now what I want to do? I want to bring the next 0 here. Then ones are 1 1 0 1. Odd number of ones 1 1 0. Then I'll get this 0 here. Okay, 1 1 0 1 1 1 it is 0. It is 0. 1. So I will bring this 0 here. Bring this 0 here. Then see here. I have only 1 1 0. So it is 0 0 0 0 and 0. I'll rewrite here. I have 0 0 1 1 0. So 1. Okay. Now 1 1 0. I'll bring this last 0 here. So it is ones are 1 1 0 1. It is 1 0 0 and 0. Now which is my CRC here? This one. So 0 0 1 is nothing but my CRC. See here. I will explain same example once again. See here. Ones are 1 1 0 1. Okay, so both the inputs are high, so I'll write 0. It is 0 and it is 1. And I'll bring this 0 here. It is ones are 1 1 0 1. It is 1 0 1. Then I'll get this 0 here. Now ones are 1 1 0 1 1 0 1 0. Okay, odd number of ones, so 1 1 1. I'll bring this 0 here. Okay, fine. Now ones are 1 1 0 1, odd number. Okay, I'll write next odd number. Okay, fine, but here I have both even numbers, so it is 0. See here, when I have both even number of zeros or both even number of ones, what is my output? It is 0. Now I have only 0 1 1 0. Is it possible to divide? No, but I want to bring this 0 here. So what I will do, I'll write 0 here and I'll write all the zeros here. Okay, fine. Now 0 0, it is 0 only, 0 1 1 0 1 1. Okay, and I'll bring this 0 here. Ones are 1 1 0 1. Now it is 1 0, this is 0 and this one also 0. Okay, and I want to consider only the 3-bit CRC because I appended only 3 zeros. Okay, while sending data, along with the data, I'm going to place 0 0 1. At the receiver side, receiver is going to receive the data. Okay, what is the data received by the receiver? That is 1 0 0 1 0 0 0 0 1 divided by 1 1 0 1. Okay, fine. Now it is ones are 1 1 0 1. Oh, then it is even number of ones 0 0 1. Bring this 0 here. Ones are 1 1 0 1 1 0 1. Bring this 0 here. Ones are 1 1 0 1. Perform binary division. 1 1 1, it is 0. Then I'll bring this 0 here. Okay, ones are 1 1 0 1. Oh, okay, fine. Perform binary division. 1 0 1 1. So it is even number of ones 0, even number of ones 0. Okay, fine. Next I'll bring this 0 here. Then substitute all the zeros 0, 1 and 1. It is ones. Okay, I'll bring this one here. Ones 1 1 0 1. It is even number of ones 0, even number of zeros 0, even number of ones 0, even number of ones 0. I got all the zeros. So the data bits are not corrupted so that the receiver can able to accept the data. See here, same thing I have explained here also. See, ones are, I have 1 1 0 1. Okay, and I'm going to perform XOR. You must remember the XOR truth table. So what is the truth table? 0 0 0 0 1 1 1 0, it is 1 1 1, it is 0. Okay, I'm going to substitute when I'm going to have odd number of ones. Okay, when I'm going to have even number of ones and even number of 0, I'm going to substitute 0. Okay, fine. See here, odd number of ones, so 0 0 1. Bring this 0 here. It is ones 1 1 0 1. Okay, fine. It is 1 0 1. Bring this 0 here. Okay, then ones 1 1 0 1 1 1. It is 1. Okay, then bring this 0 here. 1. Now ones 1 1 0 1. Perform XOR gate or modulo 2 division. So here 1 1, it is 1 1. Then it is 0. Okay, so it is 0. So what I want to do, I want to bring this 0 here. 1. So 0 1 1 0 1. That is 0 0 0 0 1, it is 1 0 1, it is 1. So I want to bring this 1 here. So now it is 1 1 0 1. So it is ones 1 1 0 1. So I'm getting the answer 0 0 0. So my CRC value is now 0 0 0. So this indicates that the data bits are not corrupted so that receiver can able to accept the data. Now, dear student, in my today's session, I started with what is CRC. The CRC also used to detect the error. And in my next session, I'm going to discuss Hamming code. Until that, keep watching and keep learning. Thank you.